When we first learn chemistry, we are taught to see molecules as solid architecture. We map out structures like methane as rigid, three-dimensional geometric shapes held together by strict, localized sticks of energy. But scale down to the quantum level of something as simple as a diatomic oxygen molecule, and that rigidity vanishes. The electrons aren't sitting neatly between two atoms. They are smeared across a chaotic, pulsing probability cloud. The truth is, there is no single unified theory of chemical bonding that perfectly describes every scenario. Localized models excel at predicting physical 3D shapes, but they fail completely to calculate actual bond energies or magnetic states. To accurately map real-world chemical behavior, we have to treat molecular physics as a hierarchy of models. Each theory exists to correct the specific blind spots of the one that came before it. We will start by mapping spatial geometry using localized orbitals, then apply empirical corrections for specific atomic characteristics, and finally transition into the quantum mechanics required to prove molecular stability. Grasping chemical structure requires letting go of the search for one universal rule. Instead, you have to identify the precise energy thresholds where one bonding model collapses and a more complex one takes over. The foundation for mapping spatial geometry relies on a straightforward axiom. Electron pairs, possessing negative charges, despise each other. Left to their own devices, they will repel and force themselves as far apart in three-dimensional space as physically possible. This mathematical formula calculates exactly how many electron domains a central atom must manage. By taking half the sum of valence electrons, monovalent atoms, and the ionic charge, we derive the steric number. That integer dictates the base geometric family of the molecule. A steric number of 4 guarantees a tetrahedral baseline. 5 guarantees a trigonal bipyramidal baseline. The math dictates the spatial distribution. But standard atomic orbitals, s, p, and d, do not naturally point in those ideal directions. To make the VSEPR geometry work physically, the central atom must undergo hybridization, mixing its native ground state orbitals to forge new, highly directional pathways. Looking at this table of electron-pair domains, we see how the mixing of orbitals creates specific architectures. An sp3 hybridized atom with 3 bonding pairs and 1 lone pair creates a trigonal pyramidal shape, while 2 bonding pairs create a V-shape. However, not all hybrids are created equal. In non-equivalent hybrid orbitals, like sp3d, the system must manage competing forces. Because lone pairs exert stronger repulsion than bonding pairs, they immediately occupy the equatorial positions, where angles are wider, minimizing strain. Hybridization is a highly effective tool for building three-dimensional molecular models, yet it operates on an assumption of perfect, uninhibited orbital mixing, an ideal scenario that actual atoms frequently reject. Take ammonia and phosphine. Both have a central atom with 5 valence electrons, 3 hydrogen bonds, and 1 lone pair. Both have a steric number of 4. Yet ammonia has a bond angle of 107 degrees, while phosphine sits at a rigid 90 degrees. This severe deviation reveals a structural flaw in standard VSEPR application. Hybridization is an energy-intensive process. It is not a mandatory automatic behavior for every element on the periodic table. This text outlines Drago's empirical rule, which states that for compounds where a group 15 or 16 element from the 3rd period or below is bonded to hydrogen, the lone pairs generally do not participate in hybridization. For larger atoms like phosphorus or sulfur, the energy gap between the s and p orbitals is massive. Mixing them costs more energy than the resulting bonds could ever return to the system. To conserve energy, the central atom isolates its lone pair completely inside the spherical, chemically inactive s orbital. The bonds are then forced to form using the pure, unhybridized p orbitals, which naturally sit exactly 90 degrees apart. The central atom's size dictates one set of deviations, but the atoms attaching to it generate entirely different anomalies, especially when electronegativity is factored in. This passage defines Bent's rule. When a central atom bonds with highly electronegative substituents, those terminal atoms actively drain the electron density away, shifting the covalent nature of the bond toward an ionic character. To maintain stability, the central atom allocates less s character and more p character to the hybrid orbitals pointing toward the electronegative atoms. Because p orbitals are longer and more directional, they stretch further out to accommodate the unequal sharing of electrons. Spatial mapping, therefore, is governed by a strict internal economy. Geometry is dictated by the energy costs of orbital mixing and the continuous tug-of-war for electron density. Even with the empirical corrections of Drago and Bent, localized models eventually hit a hard mathematical wall. They cannot calculate precise bond dissociation energies, nor can they accurately model simple diatomic molecules. To measure actual thermodynamic survival, we must discard localized architecture and transition to molecular orbital theory. Here, electrons are not trapped between two specific nuclei. They are distributed across wave functions that belong to the entire molecule. This requires the mathematical framework of LCAO, the linear combination of atomic orbitals. These probability functions map how atomic orbitals interact. Because quantum electrons exhibit wave-like behavior, moving two atoms close together forces their individual wave functions to overlap. They will either interfere constructively, combining their amplitudes, or destructively, cancel each other out. Constructive interference creates a bonding molecular orbital. By adding the atomic wave functions together, electron probability concentrates directly between the two nuclei. This negative charge binds the positive nuclei together, generating stability. Conversely, destructive interference subtracts the wave functions, creating an anti-bonding molecular orbital. This creates a distinct nodal plane, a region of absolute zero electron probability directly between the atoms. Without electrons to shield them, the positive nuclei violently repel each other. True molecular stability is not about lines drawn on a page. It is determined purely by the ratio of bonding interactions holding the atoms together versus the anti-bonding interactions tearing them apart. We can observe the failure of localized models directly in liquid oxygen. It reacts strongly to magnetic fields. It is paramagnetic. Yet, if you draw a classic Lewis structure for O2, every single electron appears perfectly paired. This chart displays the molecular orbital energy level diagrams for second-row diatomic molecules. It is the only theoretical framework capable of resolving the oxygen paradox. Looking at the configuration for O2, the highest occupied energy level is the pi-star antibonding orbital. Here, we clearly see two isolated unpaired electrons occupying separate degenerate orbitals. Those two unpaired electrons are the definitive quantum proof of oxygen's paramagnetism. A localized model completely misses this reality. The chart reveals a secondary structural anomaly. Notice the orbital sequence for nitrogen compared to oxygen. In nitrogen, the sigma 2t orbitals sits higher in energy than the pi 2p orbitals. In oxygen, the order flips entirely. This shift is caused by sp mixing. In elements like carbon and nitrogen, the 2s and 2p atomic orbitals sit so close in energy that they interact. They repel one another, forcing the sigma 2p molecular orbital higher up the energy scale. But as we move across the periodic table to oxygen and fluorine, the nuclear charge increases. This stronger pull drags the 2s orbital far down in energy, creating a gap so wide that sp mixing abruptly shuts off, restoring the normal orbital sequence. Molecular orbital theory bridges the gap. It maps out how abstract atomic properties, like nuclear charge and wave interference, manifest as empirical realities we can measure in a lab. Look at this equation for bond order. By subtracting the number of antibonding electrons from the bonding electrons and dividing by 2, we extract a hard mathematical measurement of a molecule's dissociation energy. When mapping physical architecture and spatial distribution, VSEPR theory, refined by the empirical corrections of Bent and Drago, remains the most efficient, accurate tool available. However, to accurately evaluate bond strength, spectral emissions, or magnetic states, those geometric approximations must be entirely discarded in favor of delocalized wave functions and orbital energy levels. True chemical analysis requires utilizing both halves of the theoretical spectrum. You must know exactly how to apply localized geometry, and exactly which energy threshold demands you abandon it for quantum reality.